Alright, so in this video we go over section 3.4, building quadratic models from verbal descriptions and from data. So in this case, in this section we go over applications of quadratic functions or equations as well in many areas of actually economics, science like physics and geometry. So we're going to look at our first application with one example dealing with maximizing revenue. Well, revenue is a function that depends on the price and the quantity x of certain x quantity of x element that we sell. For example, in this case, just some product. We're not going to specify what the product is. And well, the two parts of this mathematical model, well, it's the price function and then the revenue function. All right, so revenue. Let's recall what how we find the revenue. Well, so let's say you sell sodas for a fundraising. Well, the total revenue, the total money you make, not the profit. Let's be careful with that. The revenue is multiply the price of whatever you sell those sodas for times x the number total of soda that you sell. In this case, that's just x times p. Well, in this case, price is given as a function of x. So we're going to find the model that expresses the revenue r as a function of the price x. So in this case, well, r, which is r of x, which is x times p, all we do is simply substitute or plug in, replace this expression where the p is. And that's all we do. That's about it. Alright, so that's going to be x times negative 1/3 x plus 100. And from here, all we do is distribute the x. So negative 1/3 x squared plus 100 x. So that's the first part of this exercise. Well, before looking at because we want to maximize, right? You want to maximize the revenue. Of course, you want to make the most possible. Well, how do we know that this function is going to give us a maximum? Well, if you thought because of the leading coefficient being negative, well, that is correct because this is a quadratic function whose graph is a parabola, and in this case it's opening down because the leading coefficient is negative. That means we're going to have a maximum, right? So far what we have, it's making sense. Now the domain of the function r right here. Well, so I mean, if you look at this function, it's a polynomial function. It's a quadratic function whose that actually has no restrictions at all because it doesn't have radicals with negatives inside or denominators that can make or expressions x's that make the denominator 0. So we could say, well, all real numbers to that end. However, in this case, well, the number x represents the number of the quantity sold, the number of items sold. And well, we cannot definitely sell a negative amount of items, right? Like in the fundraiser example, can you sell negative 5 sodas? Can you sell negative 17 sodas? No, you cannot definitely sell any of those. So we're gonna graph the. We're not gonna graph. We're gonna set this as an inequality. The price. So what we're gonna do here is 1/3 x. Well, actually, x squared plus 100x. We want to make this greater than or equal to 0. So we want to solve this inequality. And you might want to do the following. Well, let's factor out x. That's basically going to take us back to our original price function. And in order to solve inequalities, if you remember, well, we need to turn this into an equation. So I'm going to write this again. Set it equal to 0, turn it into an equation, and solve for x. So x equals to 0 and x, or actually negative 1/3 x plus 100 equal to 0. Well, for the first factor, we can actually discard it because we don't want to sell no items, because that's no revenue, and well, consequently no profit. Well, even though profit is really not into play here. All right, so in this case, if you want, in this case, we can go back to inequality notation, and negative 1/3 x plus 100, oh, actually, well, plus 100 greater than or equal 0, negative 1/3 x greater than or equal negative 100, and then I'm going to multiply both sides by negative 3. Multiply both sides by negative 3 to get x by itself. So x is going to be 300, but keep in mind that when we multiply a negative number, an inequality on both sides by a negative number, we reverse the inequality sign. So in this case, the domain is all numbers that are actually, in this case, we need to be very careful when we express the domain of this function. So x such that, well, not just x less than or equal 300. Keep in mind that we also need to have this greater than or equal to 0. All right, because we don't want to sell a negative amount of items, right? Well, actually, when you look at the MyMathLab homework, you will see this also as just as greater than, less than, not less than or equal without the equal part, but it's still still the same. For some reason, they don't consider this 300. The reason for which they don't consider, because if we include the 300, plug it back in, that's the price function. So if you plug in 300 over 3, that's a negative 100 plus 100 is 0. So the price would be 0, and well, that's no revenue there. All right, so that's why this one is also just less than. I just wanted to make a note on this. All right. Now let's see, what's the revenue if 100 units are sold? In other words, they're asking us to evaluate the function, the given function at 100. All right, plug in 100 on our revenue function right here. So I'm gonna write this, negative 1/3, I'm gonna open parentheses, quantity squared plus 100 times, and in this case 100. All right, so that's going to be equals to, well, punching this in the graphing calculator, we should get the following approximately, in terms of money, of course, because this is about money, 6,666 with 67 cents. If you want to pause the video so you can verify this using your calculator, go ahead, and let's move on to the next part. Part D, what is the quantity X that maximizes the revenue, and what is that maximum revenue? All right, well, so in this case, from the revenue function that I'm going to write again just so you can see it, we need to find the maximum of this function, of this revenue function. How do we do that? Well, we need to use the vertex formula. So by using the vertex formula, x equals minus b over 2a. That's the quantity that multiplies x to the first power is b. The quantity that multiplies the x squared, that's a. All right, so all we need to is plug in the vertex formula to get that. So negative 100 over 2 times negative 1/3. Be careful here. All right, negative 1/3. So what are we going? We're gonna take it from here. Well, so this is gonna be 2 times a negative 1/3. Well, actually, negative over negative is gonna be positive 100 over 2/3. Okay, keep in mind that dividing by a fraction is the same as multiplying by the reciprocal times 3/2. Simplifying this, we get 100 over 2, that's 50. 50 times 3, and that's 150. So in this case, let's call this units. They are not specifying what they are. All right, so that means that if we sell 100 units for this particular model, that this amount is going to make our revenue the maximum. All right, now we need to find that maximum revenue. Let's call this, so all we do is plug in 150 in our original function. Okay, so that's going to be negative 1/3 times 150 squared plus 100 times 150. Okay, 150 squared times 150. All right. So what do we need to do? Well, let's just put all this in the calculator. If you want to pause the video to verify that in this case we should obtain 7,500 actually. Even in this case. All right. Now let's see. Well, part A, what price should the company charge to maximize the revenue? Well, notice that this function relates only the revenue with the amount of items sold, not the price. However, what we can do in this case, well, since they're asking us for the price to maximize revenue, well, let's go back to our price function that is on the top of the page. P equals to negative 1/3 x plus 100. So what are we going to do? In this case, since this is the price that maximizes the revenue, that's the price x that that's the number, actually, not the price, that's x, the number of units that we need to sell in order to find out what that ideal price will be. So P equals to negative 1/3 times 150 plus 100. Okay, so that's let's simplify this, and that's going to give us as a price. If you want to pause the video to do this in the calculator and then verify with me that this is 50. So $50 is the price that will make this revenue a maximum. All right, let's look at another example. So for this example, projectile motion, well, we are given this another quadratic function. So let's see what the problem tells. So a projectile is fired from a cliff 500 feet above the water at an inclination of 45 degrees to the horizontal with a muzzle velocity of 400 feet per second. The height h of the projectile above the water is given, well, but we don't have to figure out the mathematical model. Well, in this case, they're giving it to us. It would be good if we simplify, because here we have negative 32 over 400 squared. You don't want to work with a number like this, so you might want to rewrite this, and if we simplify, we get this. 1 over 5,000 x squared plus x plus 500. All right. So the first question, at what horizontal distance from the face of the cliff is the height of the projectile a maximum? Well, so again, the same vocabulary is coming into play here. Max and min. Well, maximum involves to find to use the vertex formula in which x equals minus b over 2a. All right, so again, this number right here is a, and in this case 1, which is the number that multiplies the x, that's b. All right, so, and of course, not that we need it, or we might need it later, that's c. So let's plug in the numbers. So in this case, negative b, which in this case is 1, over 2 times the quantity a, which is this ugly looking fraction, negative 1 over 5,000. All right. And well, this one is going to be a little bit weird to work with. Well, that's negative over negative, that's a positive, and that's a 1 over 2 over 5,000. Right? Be careful here when rewriting this. So we're going to multiply this times a fraction. We have a number divided by a fraction. Again, multiply by a fraction is the same as multiplying by the reciprocal. 1 times 5,000 over 2. And in this case, this goes evenly as 2,500. What are the units here? Well, in this case is feet. All right, feet, 2,500 feet. Now, part B, find the maximum height of the projectile. Well, how do we find the maximum? Well, we do that by plugging in this value, 2,500, back in the original function here. All right, so in this case, the h function evaluated at 2,500 equals, that's negative squared plus x plus 500. All right, so 2,500, 2,500. What are we doing? We're plugging in this 2,500 over here in this x, this 2,500 over here in that x as well. All right, and if we use a calculator, we should get the following. Our maximum height in this case is 1,750 feet. All right. You can circle my final answer here, or rather a box. Now the tricky part right here. That part C. At what horizontal distance from the face of the cliff will the projectile strike the water? All right, strike the water. That means that's a keyword here. That's a very interesting keyword, to strike the water. So before doing any math, let's draw a little picture here. All right. So the projectile is being launched from is being fired from 500, from an initial height of 500, and it's going to do this essentially, right? So the projectile is going to go up. It's going to go up the hill. It's going to reach a maximum height, and then it's going to fall and hit the water. In this case, it's water. Okay, because this is an actual cliff, and it's so well. They're asking us essentially at what value of x it's the height h equals to 0. So in other words, for which x is h of x, our function equals to 0. That's the real question. In other words, all we have to do is set our equation, or not equation, our function, our given function, set it equal to 0, and solve the equation for x. All right, I agree. If you're thinking of solving this equation, I mean, which you might want to do if you want. This is a. Again, this is 1. That's our b, and this is c. You would have to use the quadratic formula in this case. All right. So x equals minus b plus minus the square root of b squared minus 4ac divided by 2a. All right, so let me just write it down. Let me just set it up for you. Okay, so this would be the following. So that'll be -1 plus minus the square root of b, which is 1 squared minus 4 times a, which is this ugly looking fraction, times c, which is 500. All right, and then divide the whole thing by 2a, which is 2 times -1 over 5,000. So that looks like really ugly looking to do. So I'm going to save your life here. So I mean, I'm just going to set it up. I'm not going to ask you to do all the math right here, but this just show you how it would look like. So we're going to take advantage of our graphing calculator. And in this case, what we do is let me quit here. Okay. So let's turn on our graphing calculator, and let me see if I can add some light. Yes, let me add some light so you can see the whole thing. All right, so make sure to type this this given function, and let's plot. Let's graph. All right. I'm going to show you soon how did I get this plot right here. Don't worry. All right, so in this case, well, let me actually move the that's fine. Let me move the window slightly to 560, and the y-min, let me make it -200. All right. Okay, let me graph so you can see a little bit more of it, of the whole graph. So what you want to do in this case is, well, we're looking at the value of x in which our projectile is going to hit the water, not the ground. Well, basically the water in this case, which is this. What we want to do is find the 0 of the function. So we're going to go second, the trace button, and then in this case we are looking for the 0. So 0, what we're going to do is look at this flashing star that just popped. So we need to set a left bound, and the left bound is going to be somewhere before the intersection with the x-axis. Somewhere here is fine. And then we need a right bound. We need to scroll a little bit to the right, but in this case somewhere past the intersection. So click enter. Then we need to click enter another time, one more time, to make the calculator put these two lines together and find the actual 0. And in this case the 0 is 500, 54, 58. All right, 54, 58. 54, 58. All right, 54, 58. In this case, we're looking for an integer. All right. Now, keep in mind that this is a quadratic equation. It has a positive solution and a negative solution. In this case, well, if you look at the graph, the other point in which the graph would potentially get equal to 0 is in the negative side, and in this case we don't want any negative solutions because this is a physical application. It's not like going back in time, if you will. All right, so use a graphing utility to graph the function at from 0 to, okay, let's use the window. Let's use the window here, and 0 to 500 and 5500 by 2000, 0 to 2000 with this scaling, so we can see the whole graph. Well, how do I know? How did I figure out these dimensions? Well, because sometimes it might be a little bit tricky to find a good window so we can look at the entire graph. Well, let's go back to the max and the min. I mean the max and the value of x in which x is maximum. So the value of x in which x is the maximum is x equals to 2500, basically 2500 basically here, and the maximum is 1700, is y 1750. So in this case, I just increased the window of as far as the x value. I increased it all the way to basically a little bit more than twice this value, so we can look at the entire graph. All right, and then for the y value, well, the maximum value is 1700, just slightly above, in this case 1750. So I need a slightly larger y limit so I can see the entire graph. How do we set that up? Well, we go to window, x min, x max. In this case, I increase it just a little bit so I can see the x intercept. So I actually changed that to let's see. So it used to be 20. It used to be 2000. In this case, that's now well, 550. That's 500. I mean 5600. And in this case, instead of 0, it goes from negative 200 to 2000. And that scaling, well, I scaled the x's for 500 each, and the y's I scaled it to 200 each. So if you look at the graph, each line in the x-axis represents 500, and each line in the y-axis represents 200. And that's how we get this. All right, actually, if you want to verify this max and the min, what you want to do, well, okay, let's verify these two. So what you want to do in this case is go second, trace, and in this case we're going to look for the maximum because we have a maximum. So what are we going to do? I'm going to scroll back to somewhere before reaching the max, which is here is a good place, and somewhere past the maximum point, which in this case is anywhere here is fine. And then we're going to click another time to put these two lines together and give us the actual max. And if you look at the numbers, they actually check with what we did by hand. All right. Now let's look at another part here. So it will involve solving an equation. Well, when the height of the projectile is 100 feet, how far is it from the cliff? In other words, when the projectile is, well, let's say here 100 feet, how far is it? Is actually where they're asking us for this value of when the height is 100, what is x? Right, so we need to answer that question well. So in other words, find x when h of x equals to 100. All right, so let's see. So what we need to do in this case, well, we need to go back to our original function when h of x again, that's negative 1 over 5,000 x squared plus x plus 500 equals 100. Let me leave it here. Another alternative, let me just write it down, and this is what you don't want to do. Let me save you from a lot of pain. Yes, I know what you're thinking. You're thinking of moving this 100 to the left hand side and obtain this equation. Alright? And then use the quadratic formula, plug in and obtain ugly looking expressions like this. However, I'm going to do something else instead. I'm going to show you how to get this using the graphing calculator. Alright? Well, what I would like to do in this case is set the whole left hand side as our y1 and the right hand side, let that be 100. All right. So actually, no, not 100, actually y2. Okay, this is our y2. So let's go back to the graphing calculator again. And let's go to our y equal. Okay, we already have y1 in as our projectile motion model. And I'm going to say 100 over here. Click enter. Well, not enter, actually graph. And that's what it's going to do. It's going to graph y equals 100. And what we want to do is find the intersection point between these two. All right, so this is what we're going to do. Using, let me use a different color here. Using in this case, the intersect function. This is what we do. We're gonna go second trace again, but in this case we're gonna scroll down to number 5 and find an intersection. How are we gonna do that? Well, notice the first star that just pops flashing. Just drag it a little bit as close as you can, as close as you want to this intersection point. All right, not exactly at the point, just slightly before this or after, if you will. That it really doesn't matter, but before is typically fine. And click enter. And then the second curve, we can do this. Notice how this flashing star pops for the second curve, because it's a horizontal line. It could be somewhere before or somewhere after. Well, somewhere before is somewhere before the point of intersection. That's fine. And I've just clicked enter, and you will see the word guess. Click enter another time, and that's going to give us the intersection point. All right, and in this case, we obtain, using the intersection point, we get x equals to 5,372.28. Well, actually, let's just round it to the nearest integer. 5,372 feet. All right. So what does that mean? It means that when the projectile, the projectile will have a height of 100 feet when horizontally is 5,372 feet. All right. And this pretty much concludes this problem. However, I would like to extend this just a little bit. Well, let me add a part F. So part F, what about, okay, same question as in E, but instead of 100 feet, let's add, what about 430 feet? because this is going to be a little bit different. Well, I mean, we're essentially doing the same, but it's going to look when we set up the equations. So, well, first we need to set up the equation. So that is negative 1 over 5,000 x squared plus x plus 500 equals 430. And I know, same, you might want to move the 430 to the other side, but yeah, you don't want to solve the quadratic equation. If you want to do it on your leisure time by hand, that's fine. So just so you can verify the results, we're going to take a slight shortcut, and we're going to do it using the graphing calculator. So I'm going to replace the 100 with a 430. So that's going to be our y2. Okay, let me just go back over here. That's again our y1, and this is our y2. All right, so I just replaced that, and I'm going to graph again. Okay, so the first is the parabola for the projectile motion, and now we're gonna get that. Actually, I don't think I think I need to add more than 430. Let me tweak, because otherwise it's not gonna work the way I wanted it to work. Let me add 520. Let me see if that works. Okay. I thought it was gonna work with 430. No, maybe not. Not even 530. Let me add 570. Hopefully this actually the maximum height. Well, let me actually 670. Okay, 670. Let's hopefully something interesting works out here. Let me add 200 more. 870. That should be better. That should be a better picture for what I want to do in this case. Okay. Yeah, that's better. So let me 870. 870. Okay. 870 feet. So what I want you to see in this case is that, as opposed to the previous example, the 100, in this case for 870 we have to intersect. So this is going to happen twice in the trajectory of the projectile. So the projectile will be 180 feet high when the horizontal distance is actually in two places. Once when it goes up, and a second time when it goes down. So we're gonna find both of this. So I'm gonna go again, second trace, intersect, and in this case, well, I'm gonna move the flashing star here to somewhere before the intersection. Click enter, and for the second curve, rather the line, that's good enough. Notice that's before the intersection, and click enter, and then click enter a third time to find the intersection point. So in this case, well, x is approximately 402. Let me just go with integers. So x1 approximately 402 feet, and x2, we're gonna find out what about x2. So for x2, I'm gonna do this process again. Second trace, another intersect, but I'm gonna move all the way, this time past. I highly recommend you do past the intersection point, so the process is done towards the left, and find this point, right? So I'm gonna click enter for the first curve. Second curve, oh, it was really nice to move it to the right for me, and I clicked enter. Let me click after when you click enter the second time, you'll see this word guess, and then click enter the third time, and that's gonna be 4,500. 97.6. That I'm gonna round that using the rounding rules. I'm gonna round that up to 45.98. All right, feet. So 2 answers in this case as opposed to the previous one. And the reason why I did this extension is because when you do the homework, you may get something that may require you to use the intersect function only once or maybe twice. All right. So who knows what's gonna come in on the homework. So, but it's important to be prepared with both of this. All right. So now let's look at the third application, maximizing the area. All right. So in this case, what are we going to have? All right. So David has available 400 yards of fencing and wishes to enclose a rectangular area. Express the area A of the rectangle as a function of the width W of the rectangle. All right. Actually, this type of problem will come up in calculus later. So we're gonna solve this problem the algebra way. When you get to calculus, you're gonna do other kinds of operations. If you have taken calculus in before, well, I think you have an idea of what we're talking about. In the meantime, okay, let's draw a rectangle. All right, the rectangle has some length and some width. All right. So we need to express the area as a function of the width. Notice in this case, if we write down the area function, that's length times width. But wait a minute, this function has 2 variables. And they're asking us to write this in terms of one single variable. Well, what do we know? What do we need to do? Well, we need to use the given information to get rid of some of the variables. What kind of information are we going to use? Well, so this, if I do the following, this is the perimeter of the rectangle, and these 400 yards will actually make what the perimeter is. So in other words, perimeter equals, if we recall the formula for the perimeter of a rectangle, that's 2 times the length plus 2 times the width. Okay, so what are we going to do in this case? Well, we know the numerical value of the perimeter, which is 400. And what we're going to do, so I want to have our area function in terms of only W. That means I need to get rid of L. How do we get rid of L? So what we're going to do here is solve for the variable L in this equation. I'm going to subtract 2W from both sides. And boom, boom, they go away. And 2L equals 400 minus 2W. And then finally solving for L by dividing both sides by 2. That's going to give us L equals 400 divided by 2. That's really nicely divisible. 2 over 2, that's just 1 W. So what am I going to do here? Well, so I'm going to box this, and this is going to be substituted here. All right. This marker is dying on me. Okay. And so area that now depends only on the width W is this quantity 200 minus W times W. All right. But in this case, well, we need to make this look like a quadratic function. So what we do is distribute the W, and that's going to give us A of W equals W times negative W. Well, that's negative w squared plus 200 w. So that's part A of this of this third example. Okay, so for what value of w is the area the largest, and then what's the maximum area? All right, well, this is going to lead us again to a vertex formula. Well, looking at this function again, well, it has a negative leading term. That means it's a parabola opening down, giving us a maximum. So all we're doing right now, it's checking. So minus b over 2a. In this case, well, w, not x, because the variable is it's w. So let's call a equals to -1 because that's the leading coefficient. -1 and b equals 200. I don't think we need to, well, c would technically be 0, but we don't even need c in this case. So let's plug in the numbers, and minus b, which is 200, over 2 times a, which is -1. Negative over negative is positive, and then 200 over 2, that's 100. In this case, well, they're yards actually. I thought we were not given the unit, so it's yards. What is the maximum area? Well, what do we do in this case? Plug in this 100, evaluate it in this quadratic function, in this function that gives us the actual maximum. All right, so let's go ahead and do that. So a evaluated at 100, it's going to give us negative w squared plus 200 w. All right, so using a calculator, in this case, we are going to get as a final answer 10,000. And be careful with the units, because the units for length are just yards, but the units for area are going to be yards squared. All right, and this is final answer and a good place to quit this video. All right, I'll see you in the next section.